So now this is about a moving coil galvanometer. So in the case of moving coil galvanometer, let us see the rough construction of it. It consists of a rectangular coil wound over a soft iron core. This is the soft iron core. Okay, and the rectangular coil is suspended by means of a phosphor bronze wire. This is a phosphor bronze wire in which there is a mirror and scale arrangement. The mirror is seen here, and then it is attached to a torsion head. So, and the entire apparatus is placed in vacuum between the poles of a radial magnetic field, a north and south pole, and the entire apparatus is placed, and it is also placed in vacuum, where you have leveling screws T1 and T2 to make the leveling adjustment, and a T3 and a T4 to make any external connections. So this is the basic structure of the moving coil galvanometer. And to be more precise, if you see that the radial magnetic field is going to be like this. This is the top view of the radial magnetic field, and this is the north pole and the south pole. And you know that the outside the bar magnet, the magnetic field is from north to south. And this is the top view, and a top view from where you can see the coil. The coil is also in the same direction. The angle between the magnetic field and the length of the wire is theta is equal to 0 here. So ideally, in this derivation, if there is a pointer here, the pointer will move around a calibrated scale for you to see the how much is the wire being twisted, because this is coil. How much ever the wire is getting twisted, how that much the tilting of the coil will also happen, and the rotation of the coil will happen. And so then, therefore, you should start the derivation with torque is equal to niba cos theta, because here cos 0 is 1, and the angle between the magnetic field and the coil of the wire itself is 0. Theta is equal to 0. uh, Torque is equal to niba, and torque itself is also proportional to angle of twist of the wire. We can call the angle of twist to be alpha or theta, whatever. So T is equal to C into alpha, where C is called the couple per unit twist. Couple per unit twist. And so then we can equate this niba with C alpha. So C alpha is equal to NIBA. So I is equal to C alpha by NBA. And the purpose of the galvanometer is to show deflection, large deflection for a small current. This is possible only when the couple per unit twist is less, number of turns is more, the magnetic field strength is more. Of course, area of cross section is more, but they'll make the apparatus bulky, so let's not count that. So then you can current for a small current, large deflection is possible by making sure the couple per unit twist is less, and of course number of turns is more, and magnetic field strength is more. So this is why we choose a phosphor bronze wire. A phosphor bronze wire is an alloy. Bronze wire is an alloy, and so it doesn't get oxidized easily. Doesn't get oxidized easily, and then tensile strength will be very high. Tensile strength will be high, and the point is couple per unit twist is less, and these are the factors why we choose phosphor bronze wire to hang the rectangular coil wound over a soft iron core. So this is the basic thing. And so let's talk about current sensitivity. Current sensitivity is IS, which is a deflection per unit current, and voltage sensitivity is deflection per unit voltage. You already know what is I from the first equation, substituting there. Alpha is equal to C alpha NBA. Alpha get cancelled, but the current sensitivity is NBA by C. Whereas this is IR, and substituting again for I, you get NBA by CR. The question, this is voltage sensitivity. Normal question comes in association reasoning, where they'll talk about when the number of turns is increased, the current sensitivity also increases. Whereas the number of turns is increased, the voltage sensitivity does not increase, because proportionately the resistance also increases, contributing to nothing is affecting the voltage sensitivity. So this is very important. So next is about how to convert a galvanometer into an ammeter. Let's look at the property of an ammeter. Ammeter has got in generally low resistance, and the voltage in general has got high resistance. The fact that this has got high resistance and this has got low resistance, you can convert. Supposing in your lab the ammeter or voltmeter is not working. Okay, voltmeter is not working. What you can do is take a galvanometer, and you want to make sure that the resistance is increased to convert into voltmeter. So connect the resistance R in series, which means is Ig into G. plus Ig into R. Ig into G plus Ig into R is going to give you the entire voltage V. And so then if you want to know this unknown resistance that has to be connected here R, it's V minus Ig into G by Ig, and this is the formula. And this is how you can connect the resistor in series so that the galvanometer can behave like a voltmeter. And supposing you want to convert a galvanometer into an ammeter, you connect a low resistant S shunt in parallel, low resistance shunt. In that way, when you can, it's 1 by G plus 1 by G resistance decreases, and so it behaves like an ammeter. In that case, the current that's coming in goes in as Ig, and this goes as I minus Ig, and voltage across above and below is going to remain the same. So you can write Ig into G is equal to I minus Ig into S. So this unknown shunt value, the low resistance value, is Ig into G by I minus Ig. Thus, you can figure out what should be the resistance that should be connected. If you know the galvanometer current, the resistance of the galvanometer is G. I is the maximum current that can flow through the galvanometer, and Ig is the current that's flowing at that instant. So then all these values, okay, I is the current that's flowing in the circuit, and Ig is the current that's coming into the galvanometer. So when you know all these values, you can talk about how to convert a galvanometer into an ammeter and a galvanometer into voltmeter. There are many numericals based on this, and with this completes the lesson.